Fourier Sine Series. Now for sine series, we are going to be dealing with odd functions. Okay, and in odd functions, f of minus x is equals to minus f of x, and thus it will only contain sine function. That is, a0 is equals to 0, an is equals to 0, but then we have a formula for bn. So the series is represented with this, and all we just have to do is evaluate bn. So we are given f of x is equals to x cubed. We can check if it is a sine series or a cosine series by testing if it is an even function or an odd function. So if f of x is equals to x raised to power 3, then f of minus x is equals to minus x raised to power 3. And minus x raised to power 3 is minus x times minus x multiplied by minus x. And this will give us minus x raised to power 3. Now, this is the same thing as minus f of x, because f of x in itself is x raised to power 3. Okay, so since we know it is a sine function, an odd function, obviously a sine series, so all we just have to evaluate is bn. So bn, according to the formula, is 2 over pi integral of 0 to pi f of x sine nx dx. Now we impute our f of x, okay, to be x raised to power 3. So bn is 2 over pi integral from 0 to pi x raised to power 3 sine nx dx. Now to solve this, we move in terms of uv, okay, where u is equals to x raised to power 3 and v is equals to sine nx. And we duly recall that integrating function, two functions u and v, to be u v1 minus u prime v2 plus u double prime v3 minus u triple prime v4 plus u iv v5 minus, it continues in that order. So given u is x raised to power 3, our u prime, which is differentiating x raised to power 3, is 3x squared. Differentiating it further again, we have it to be 6x. Differentiating it further again, we have it to be 6, and this will give us 0. So we have to evaluate v1 down to v5 or v4, down to v4. So v1, which is integral of v with dx, is integral of sine nx, and integrating sine nx with dx, we have it to give us cos nx over n. v2, which is integral of v1 dx, and v1 is cos nx over n. Integrating cos nx over n, we have minus sine nx over n squared. Moving on, we have v3, because we are evaluating up to v4. v3 is integral of v2 dx, and v2 is minus sine nx over n squared dx. Now integrating minus sine n squared over n squared, integrating minus sine n x over n squared will have it to give us cos nx over n cubed. And v4, which is integral of v3 dx, is integral of cos nx over n cubed dx, and this will give us sine nx over n raised to power 4. Now the next thing to do is to follow and solve bn. Bn is 2 over pi. Now integrating uv, we have u x raised to power 3 v1 minus cos nx over n minus u prime 3x squared v2 minus sine nx over n squared plus u prime prime 6x and v3 cos nx over n cube minus u triple prime 6 and v4 sine nx over 4 n raised over 4. This is from a limit of 0 to pi. Now, simplify further, we have bn to be 2 over pi minus x raised to power 3 cos nx over n plus 3x squared sine nx over n squared plus 6x cos nx over n cube minus 6 sine nx over n raised to power 4, 0 to pi. Hereafter, we implement our upper limit minus lower limit. The upper limit is pi and the lower limit is 0. So we have 2 over pi. So we put our upper limit of pi. So wherever of cx we put pi cos n pi over n plus 3 pi squared sine n pi over n squared plus 6 pi cos n pi over n cube minus 6 sine n pi over n raised to power 4. Then we add our lower limit of 0 into this function as we've done for pi. So wherever of cx we put 0 minus 0 cube cos n of 0 divided by n plus 3 multiplied by 0 squared sine n of 0 multiplied by n squared plus 6 into 0 cos n of 0 divided by n cube minus 6 sine n of 0 divided by n raised to power 4. Now, having done this, we recall that sine n pi is equals to 0 and sine n of 0 was also equals to 0. So this contains sine n pi. So this is going to turn to 0. Okay, this also contains sine n pi. So it turns to 0. This is multiplied by 0, turns to 0. This term is also multiplied by 0, turns to 0. Same thing here. And this contains sine n of 0, and sine n of 0 is 0. So we are left with this, and we are also left with this. And they both contain cos n pi. And we know that cos n pi can either be plus 1 or minus 1, depending, okay, on n. It is plus 1 when n is even, and it is minus 1 when n is odd. So simplifying this further, Bn is equals to 2 over pi. We add the terms that are left as minus pi cube cos n pi over n plus 6 pi cos n pi over n cube. Now with this done, we can now begin to evaluate values of b1, b2, b3 and also b4. Okay, so in this case b1, that means n is equals to 1. We have 2 over pi minus pi cube cos 1 pi, n is 1, plus 6 pi cos n, n is 1, pi divided by 1 raised to the power 3. Now we have it to give us 2 over pi minus pi cube cos pi is minus 1. Everything divided by 1 minus 6 pi, and cos pi also is minus 1 divided by 1. So we have 2 over pi into pi cube over 1 plus 6 pi. This is plus, sorry, minus 6 pi over 1. So let's divide all through by pi. That will be left with 2 into pi squared minus 6. This is b1. Now when we do the same thing for b2, b3 and b4, okay, we have b2 to be 2 into minus pi squared over 2 plus 3 over 4, and b3 to be 2 into pi squared over 3 minus 2 over 3, and b4 to be 2 into minus pi squared over 4 plus 3 over 32. Now we have b1, we have b2, and we have b3 and also b4. And we recall that f of x is summation of n is equals to 1 to infinity bn sine nx, because we are dealing with sine series, and in sine series a0 is 0, an is also equals to 0. So splitting this individually, we have b1 sine x plus b2 sine 2x plus b3 sine 3x plus b4 sine 4x. So we have f of x to be equals to b1 is 2 pi square minus 6 multiplied by sine x plus b2, okay, b2 is this 2 into minus pi squared over 2 plus 3 over 4 multiplied by sine 2x plus b3 is 2 into pi squared over 3 minus 2 over 3 multiplied by sine 3x, and b4 plus 2 into minus pi squared over 4 plus 3 over 32 multiplied by sine 4x. Now with this, we have been able to solve the question of representing f of x is equals to x cubed using Fourier Sine Series. We also pick another question of Fourier Sine Series in the next video.